Good day. My name is Andria Trigeorgi. I'm a PhD student at the University of Cyprus. I'm going to talk about how to boost concurrency of shared large objects using a fragmentation strategy. Data are rapidly generated through applications, social media, browsers, and so on. The big question that arises is how to share this data robustly in a message passing system. So, distributed systems are being used to manage this data. First, I will introduce the main challenges for distributed shared storage systems. Data scalability, data replication, storage efficiency, communication overhead, concurrent access, and consistency semantics. Data replication is used to support data survivability and the availability of the system. Concurrent access is how the system manages concurrent access to data. Consistency is how multiple users are getting access to the same file at the same time. Linearizability is a strong consistency model where accesses are ordered according to a global timestamp. For example, if the timestamp of operation 1 is smaller than the timestamp of operation 2, then the operation 1 must occur before operation 2 in the sequence seen by all processes. However, concurrent access to shared data may result in data inconsistency. So we must find the trade-off between the consistency of the data and the availability of the system. The first distributed storage emulation was proposed by Andria, Barnoi, and Dove. They assume a single writer and multiple readers. During a write operation, the writer increases its local timestamp and sends the timestamp value pair to every server. Each server stores this latest timestamp value pair and sends an acknowledgement. The writer returns after receiving acknowledgements from a majority of servers. The read operation has two phases. One phase to find the maximum timestamp value pair, and the second phase to propagate it to all servers. The read operation completes and returns the latest value. Lynch and Schwarzman proposed the multi-writer solution. The write operation is completed in 2 rounds, as in the read operation. This happens in order to find the maximum timestamp among server replies before proceeding with the propagation phase. The MBD algorithm was extended by many works. The issue with these emulations are that they can handle small size objects, but cause performance overhead when handling large objects. Also, if 2 writes occur concurrently on different parts of the object, only one of them prevails. Erasure-coded approaches rely on the division of a shared object. During a write operation, shared data strips across multiple disks as datum disks and paradigm disks. During a read operation, data on a failed disk are regenerated using data from paradigm disk and surviving datum disk. But the reads and writes are still applied on the TR object. Distributed storage systems use data stripping in order to handle the big objects. However, the device strategies which provide weaker consistency guarantees. For example, Dropbox creates conflicting copies and guarantees eventual consistency, which is weaker than linearizability. HDFS and Blockseal ensure strong consistency using centralized modules. So we want a system that provides concurrent access to its clients without sacrificing strong consistency, nor using centralized components. The purpose of this paper is to develop a robust and strongly consistent distributed storage system, which enables different updates to occur on different fragments of the object concurrently, while ensuring that all modifications are valid. Let me summarize what we have accomplished. We built a distributed file system with fragmented objects called CombFS. Each object is fragmented into blocks. This allows big amounts to be distributed all over the servers. Also, avoids contention for concurrent accesses to different blocks. Each block is linearizable and coverable. These two notions will be explained in a while. So each fragmented object is a list of blocks. The first block is the genesis block, and each block has the ID of its next block. As we can see in the first figure, we treated the whole object as atomic. So the read operations return value according to the time ordering of the read operation of the whole object. But treating the fragmented object as a whole atomic object can be expensive and impact concurrency. So in the second figure, we invoke one operation per block. According to the time ordering of the block read operations, block linearizability is preserved if the first read returns D0 prime and D1, while the second read returns D0 and D1 prime. But this violates the linearizability of the whole object. In order to allow such executions, we introduce fragmented linearizability on the fragmented object, which relies on the fact that each individual block is linearizable. Fragmented linearizability guarantees that all concurrent operations on different blocks prevail, and only concurrent operations on the same blocks are conflicting. Looking at the third figure, consider two reads, where read 1 is completed before read 2. Then, for each block belonging in both sequences, each value returned by read 2 is the same or newer than the one returned by read 1. The coverability notion extends linearizability with the additional guarantee that an update succeeds when the writer has the latest version of the block before updating. Otherwise, an update becomes a read and returns the latest version with its value. For example, in the figure, the second write fails since the writer has version 0, which is an older version. This happens because the first write is already completed, thus changing the version of the block to version 1. In order to ensure consistency in our system, we use the coverable version of multi-writer, multi-reader embedding. The basic architecture of our system is composed of two main modules, the fragmentation module and the distributed shared memory module. As we said above, the emulation we use in the shared memory module is the coverable embedding. Following this architecture, clients can perform operations passing commands through command line interface. Then the fragmentation module uses the distributed shared memory module as an external service to execute these operations on the shared memory. To this respect, our system is flexible enough to utilize any distributed shared object algorithm. Now, we describe how the write operation works in our system. First, we split the file into blocks based on its contents using wrapping fingerprints. This rolling hashing algorithm uses a sliding window in order to identify the block boundaries. The algorithm allows you to specify the minimum and maximum block sizes, avoiding blocks that are too small or too big. Then we have to match each hash generated by the wrapping fingerprints from the previous step to a block identifier. At first, we use a string matching algorithm to find the differences between the new hashes and the old hashes in the form of 4 statuses: equality, modified, inserted, and deleted. Based on the hash statuses, the blocks of the fragmented object are updated. In the case of equality, the new hash is equal to the old hash, so no update operation is performed. In the case of modification, an update is performed to modify the old data of the block to the new ones. In the case of insertion, an update is performed to create the new blocks, and then deleted status is treated as a modification that sets an empty value. Now we describe how the read operation works in our system. Fragmentation module issues a series of block read operations, starting from the genesis block and proceeding to the last block by following the next block IDs. As blocks are retrieved, they assemble in a file. We also apply a read optimization in the distributed shared memory module. In the first phase, if a server has a smaller tag than the reader, it replies only with its tag. The reader performs the second phase only when it has a smaller tag than the one found in the first phase. Finally, I will show some evaluation results of our system. We wanted to compare the performance of CombFS and CombD, which does not use the fragmentation module. In the first scenario, we examine the performance under various numbers of readers, writers, and servers. As we can see in the first two figures, the update operation latency in CombFS is always smaller, as each writer has to update only the affected blocks. Also, the number of successful writes of CombFS is greater. In the third figure, due to the higher percentage of successful file updates achieved by CombFS, reads retrieve more data compared to reads in CombD, which explains why it is lower than CombD. In the second scenario, we examine the performance when using different initial file sizes. In the first graph, the update latency of CombFS remains at extremely low levels, although the file size increases. The second graph shows that the main factor that significantly contributes to the slight increase of CombFS update latency is the fragmentation module computational latency. In the third graph, the read optimization decreases significantly the CombFS read latency, since it is more probable for a reader to already have the latest version of some blocks. On the other hand, the CombD read latency increases sharply even when using the read optimization. This is due to the fact that each time a new file version is discovered, CombD sends the whole file. In the third scenario, we examine performance under different block sizes for our algorithm. Both graphs show that further increase of block size forces the decrease of the CombFS latency. Also, with a larger number of blocks, the probability of two writes to collide decreases. Thus, we have better success rate. I will conclude with the main goal of this research. Our algorithm CoBFS has the following advantages. Allows high concurrent accesses, provides strong consistency, and can handle large file sizes. For a future work, it will be good to perform a comprehensive experimental evaluation of our algorithm. Find a mechanism for the selection of the appropriate block sizes. Investigate other fragmentation strategies. And we want to create a fully functioning distributed file system with strong security guarantees. We can also provide an open API in which people could integrate their own distributed shared memory modules. Thanks for your attention. For any further question, you can communicate with me and my partners.